Anatomical consistency is crucial in medical image segmentation, as it directly affects the accuracy and reliability of segmentation results. Traditional pixel classification-based models often focus on categorical features such as boundaries, neglecting directional information within the latent space. To address this limitation, a novel approach, DeepNet, is proposed, incorporating pixel connectivity from digital topology into deep learning networks. DeepNet utilizes a directional connectivity modeling scheme to capture and utilize directional information across the network. This is achieved through disentangling categorical and directional features in the latent space, followed by fusing them in a projected shared manifold. By doing so, DeepNet decouples and tracks directional information, leading to more accurate and anatomically consistent segmentation results. Experiments on various public medical image segmentation benchmarks demonstrate the effectiveness of DeepNet compared to state-of-the-art methods. The results highlight the potential of this approach to improve spatial coherence and anatomical consistency in segmentation tasks, particularly in high-noise, artifacts medical data. The implications of this method are significant, as enhanced accuracy and reliability of segmentation results can substantially impact downstream clinical decision-making processes. The proposed method has been evaluated on several public benchmarks, showcasing its robustness and generalizability. The availability of the DeepNet code enables researchers to further explore and build upon this approach, paving the way for future work in enhancing anatomical consistency in medical image segmentation. Medical image segmentation is significantly enhanced through a novel approach leveraging connectivity masks and disentangling the directional subspace from the shared latent space in deep learning networks. The proposed network, DeepNet, employs a subpath slicing-based module called Subpath Direction Excitation, SDE, to disentangle the directional subspace, thereby enriching data representation. This is achieved through an interactive feature space decoder, IFD, which facilitates the extraction of meaningful features. To address data imbalance issues prevalent in medical datasets, the authors introduce a novel size density loss (SDL) function. This innovation enables the network to effectively handle class imbalance, a common challenge in medical image segmentation tasks. The paper provides a comprehensive review of related work in deep connectivity modeling, latent space interpretation, and self-attention mechanisms. This overview contextualizes the proposed approach within the broader landscape of medical image segmentation research, highlighting the novelty and significance of DeepNet. By disentangling the directional subspace and leveraging connectivity masks, DeepNet achieves enhanced performance in medical image segmentation tasks, offering a promising solution for clinicians and researchers. The proposed DeepNet model is composed of three primary components: a pre-trained ResNet encoder, a subpath direction excitation module, and an interactive featurespace decoder. This model aims to enhance feature representation in connectivity-based networks by effectively disentangling and utilizing the directional space. In these networks, there are two groups of features in the latent space: categorical and directional. However, these two subspaces are highly coupled in a single-path connectivity network, resulting in low discriminative features. To address this issue, the authors introduce the concept of SDE, subpath direction excitation, to separate the directional features from the latent space, followed by IFD, interactive featurespace decoder, to extract and enhance the directional embeddings at different layers using self-attention mechanisms. The SDE module begins with extracting directional information from the auxiliary connectivity output, which is obtained by upsampling the last encoder output to the input size and then applying a global average pooling to squeeze the channels. This process results in a vector, V% and containing rich elementwise directional information. A 1x1 convolution and a sigmoid gating function are applied to normalize the projected vector, resulting in the directional prior, alpha% and. To further disentangle the categorical and directional subspaces in the hidden layers, the authors employed channel-wise slicing to split the latent features and the directional prior into 8 parts. This step allows for the efficient manipulation of the directional features in the network. The subpath excitation, SPE, is constructed by using the sliced latent features and directional prior as inputs. The SPE module utilizes channel-wise operations to capture and manipulate the directional features, enhancing the overall feature representation in the network. The extracted directional embeddings are then used to enhance the feature representation in a self-attention manner through the IFD module. The proposed DeaconNet model aims to improve the feature representation in connectivity-based networks by effectively disentangling and utilizing the directional space. By introducing the SDE and IFD modules, the model can better capture and manipulate the directional features, leading to enhanced performance in various computer vision tasks. The Interactive Feature Space Decoder, IFD, is a novel architecture designed to effectively fuse direction-dependent information into feature maps in each layer. It consists of two top-down dynamically interactive flows, namely, space flow and feature flow, as illustrated in Figure 6. In each layer of the IFD, there are two types of feature maps: the main feature map D and the direction-enhanced map R. These maps are initialized as the outputs of the spatial-wise directional embedding, SDE, module, where D equals R equals E234. The SDE module involves three steps: direction prior extraction, channel-wise slicing, and subpath excitation. Specifically, each feature embedding slice is passed through spatial and channel attention modules to capture long-range and interchannel dependencies, resulting in E$0. The output is then channel-wisely multiplied with alpha%, and, to selectively highlight or suppress features with specific directional information. The output is then recoded with a 1x1 convolution kernel W1 foot, and the residual output is computed as E234 equals W1 foot, alpha%, and bullet operator E$ plus E$. This process is repeated for each subpath, and the outputs are stacked to form a new feature map E234. Due to the slicing operation, each group of slices will only contain part of the full features. The shrinkage of discriminative contextual information in directional and categorical features differs, with directional features experiencing significant shrinkage and categorical features experiencing less shrinkage. This results in each subpath focusing on the dominant features, with the network learning to focus on class-specific information with less distinctive directional information emphasized in the channels. Between subpaths, the network learns different distinctive directional information, which is then naturally disentangled from the original latent space and embedded into the channels. In the space flow of the IFD, a space block, S, is used to enhance the directional representation. The space block contains an embedding squeezing, S, module and a manifold projection and enhancement, MPE, module. The ES module takes R as the input and outputs a directional embedding N, which is then used as the input of MPE to enhance the directional representation in the main feature map D. The paper presents a novel neural network architecture, DeaconNet, which integrates both spatial and channel-wise attention mechanisms to enhance the segmentation accuracy of medical images. This model is designed to address the challenges posed by imbalanced datasets and varying spatial resolutions in medical imaging. DeaconNet consists of three key components: a spatial attention module, a channel-wise attention module, and a feature flow module. The spatial attention module utilizes a multi-scale pyramid pooling strategy to capture contextual information from different scales. This is achieved through a space pyramid pooling block, which aggregates features from various scales and spatial locations, resulting in a spatial attention map that highlights the importance of each spatial location in the image. The channel-wise attention module aims to select relevant channels in the feature map that are essential for segmentation. This module uses a channel pyramid pooling block to gather channel-wise information across different spatial locations. The resulting channel attention map indicates the significance of each channel in the feature map. The feature flow module combines the outputs from both spatial and channel-wise attention modules to refine the segmentation results. It consists of a feature block that includes two convolutional layers and an upsampling layer with a skip connection. This top-down design allows for dynamic interactions between the two flows, enhancing the segmentation accuracy. The paper also introduces a novel imbalanced loss function called size density loss, which considers the label size distribution of classes in the dataset. This loss function adapts to the imbalanced nature of medical data and helps in improving the segmentation performance on smaller classes. Experiments were conducted on 3 diverse medical benchmark datasets: Retouch, ISIC 2018, and CHASEDB1. These datasets were chosen to evaluate the performance of DeaconNet for large-scale medical segmentation and topological performance. The evaluation metrics used include volume-level dice, image-level dice, absolute volume difference, and volume-wise balanced accuracy. In this research, the authors introduce a novel neural network architecture named DeaconNet, which is designed to address the challenge of segmenting retinal fluid regions and skin lesions in medical images. The proposed model utilizes a new loss function, known as the surface loss, that encourages topological connectivity in the segmentation process. This approach aims to improve the accuracy and consistency of segmentation predictions, particularly for small fluid regions. The authors compared DeaconNet with 8 state-of-the-art models on the Retouch dataset, including DeepLab v3+, UNet, Attention UNet, CNet, NNUNet, CPFNet, CPFNet backbone curvature loss, and MSTGA-Net. The results show that DeaconNet outperforms all competitive models, demonstrating superior performance in terms of dice similarity coefficient, DSC, DSC with Hausdorff distance, DSC, and boundary accuracy, BACC. A qualitative study is also conducted, comparing DeaconNet with the top 6 baselines. The results indicate that DeaconNet makes accurate predictions on small fluid regions, while other methods miss or misclassify them. Furthermore, DeaconNet produces topologically connected predictions for PED and accurately segments IRF and SRF regions, where other methods fail. Additionally, the authors evaluate DeaconNet on the ISIC 2018 skin lesion segmentation benchmark, comparing it with UNet, BCD-UNet, CNet, NNUNet, HiFormer, CPFNet, FATNet, and MSRED. The proposed model achieves the best performance among all competitive models, showcasing its versatility in different medical image segmentation tasks. The experimental details are provided, including the use of ImageNet pre-trained ResNet as the encoder, varying hyperparameter settings across datasets, and the application of a poly-learning rate strategy for the Retouch dataset. The framework is built on PyTorch 1.7.0, and all experiments are performed with a GPU NVIDIA GeForce GTX 3090 Ti. The study highlights the importance of incorporating topological connectivity in the segmentation process, particularly for small fluid regions, and demonstrates the effectiveness of the proposed DeaconNet model in improving the accuracy and consistency of segmentation predictions. The authors present the results of their proposed model, DeaconNet, on 2 datasets, ISIC 2018 and CHASEDB1. In comparison to several state-of-the-art methods, DeaconNet outperforms them in both segmentation and topological vessel segmentation tasks. On the ISIC 2018 dataset, DeaconNet achieves a higher dice similarity coefficient, DSC, intersection over union, IOU, accuracy, ACC, precision, recall, rec, and F1 score than other models, including UNet, BCD-UNet, CNet, NNUNet, HiFormer, CPFNet, FATNet, and MSRED. Visualization results demonstrate that DeaconNet accurately segments lesions even under strong clinical confounders and preserves the topology of skin lesions, which is crucial for anatomical consistency. For the CHASEDB1 dataset, DeaconNet surpasses top-performing methods such as UNet, @UNet, GTDLA, CNet, CL dice loss, and graph cut loss. The model achieves a higher CL dice, DSC, IOU, and better beta-I and beta metrics, indicating that it maintains the topological similarity between predictions and labels. Visualizations of the segmentation results further support these findings, showing that DeaconNet produces more anatomically consistent predictions compared to other models. An ablation study was conducted to evaluate the contributions of different components of DeaconNet. The study reveals that both connectivity and directional modeling significantly improve the model's performance, especially in terms of DSC. Adding the spatial distribution loss, SDL, further enhances the model's performance, demonstrating the impact of the distribution-based weighting scheme. Experiments were also conducted to test the importance of the directional prior in the SDE module and the effectiveness of subpath attention units in capturing the dependency between contextual unvenly sliced directional and categorical features. These studies confirm the importance of these components in enhancing the model's performance. The authors conduct an ablation study on the directional prior, presenting the results in Table 5. Incorporating the prior improves the model's performance, increasing the dice similarity coefficient, DSC, from 86.3 to 87.7 and decreasing the average volume difference, AVD, from 0.023 to 0.020. In Table 6, the effectiveness of the subpath attention mechanism is evaluated by comparing it with alternative attention modules, including dual attention, DA, and non-local, NL, modules. The results demonstrate that the proposed subpath attention mechanism outperforms the other modules, achieving a DSC of 87.7 and an AVD of 0.020. To visualize the disentanglement of the directional subspace, the authors employed T-distributed stochastic neighbor embedding, TSNE, to project the learned patchwise feature maps in the latent space before and after the subpath decomposition, SDE, module. The results, shown in Figure 2, indicate that the SDE module decouples the latent space, leading to a polarized distribution of the latent features. The authors also visualize the learned channel embeddings in the latent space before and after the SDE module in Figure 10. The results demonstrate that the channel embeddings naturally group into several distinctive parts after applying SDE, indicating the effectiveness of the subpath excitation mechanism. In a pixel classification-based segmentation setting, the authors compare the proposed size density loss, SDL, function with alternative loss functions. The results, presented in Table 7, demonstrate that SDL achieves the highest DSC and exhibits more stability when dealing with imbalanced medical datasets. Finally, the authors analyze the model size and parameter count of DeaconNet, comparing it with the backbone network. The results, presented in Table 1 and Table 8, show that DeaconNet outperforms the backbone network with only a small increase in parameters, making 3D connectivity modeling a promising direction for 3D image segmentation. This research paper delves into the various methods and techniques employed in image segmentation, with a particular emphasis on maintaining topological correctness. It references several studies that have addressed this issue, including the use of a fast-marching algorithm for topology correction in medical images, a topological loss function for deep learning-based image segmentation, and topology preserving deep image segmentation. The paper also explores digital topology and its application in medical imaging, edge-preserved segmentation techniques, and geographic feature-enhanced networks for urban road extraction. Moreover, the authors discuss the significance of structured latent spaces for unsupervised point cloud completion, disentangling latent hands for image synthesis and pose estimation, and interpreting the latent space of GANs via measuring decoupling. The importance of cross-image relational knowledge distillation for semantic segmentation and knowledge distillation from multiscale features is also highlighted. The authors stress the importance of maintaining topological correctness in segmentation tasks, emphasizing the role of connectivity and geometric constraints in ensuring accurate results. This page provides a comprehensive overview of the state-of-the-art techniques in image segmentation, underscoring the need for topological awareness in these processes. This section of the research paper delves into various deep learning models and techniques applied to medical image segmentation, with a particular emphasis on understanding and interpreting the latent space in deep neural networks. It underscores the importance of visualizing and analyzing the feature space to comprehend how different components contribute to the final output. The authors stress the need for contextual understanding in segmentation tasks, as well as the importance of multiscale information and spatial relationships in enhancing segmentation accuracy. The paper references numerous studies that have utilized different approaches for improving segmentation performance, such as attention mechanisms, multiscale features, and contextual information. For instance, Chen et al. 2018 introduced the concept of encoder-decoder architectures with at-risk spatial pyramid pooling for semantic segmentation tasks. Similarly, Oktay et al. 2018, proposed the use of attention gates to selectively focus on relevant regions of the image during segmentation. The authors further discuss the role of transfer learning and domain adaptation in improving segmentation performance, especially when dealing with limited training data. They reference studies like Militari et al. 2016, which demonstrated the effectiveness of fully convolutional neural networks for biomedical image segmentation, and Feng et al. 2021, who proposed a deep frequency recalibration U-net for medical image segmentation tasks. Moreover, the paper emphasizes the importance of evaluating segmentation models using appropriate metrics, such as the Dice coefficient and balanced accuracy, which can provide insights into model performance. It also touches upon the idea of pseudolabel generation for semi-supervised learning, as discussed in Seibold et al. 2022. In conclusion, this section provides a comprehensive overview of the advancements in deep learning techniques for medical image segmentation, emphasizing the importance of contextual understanding, multiscale information, and the interpretation of latent spaces in neural networks. It also highlights the significance of proper evaluation metrics and the potential of transfer learning and domain adaptation for enhancing segmentation accuracy. This paper provides a comprehensive overview of cutting-edge methodologies and techniques in the field of medical image segmentation, focusing on skin lesion and retinal vessel segmentation. It discusses the importance of developing accurate segmentation models that can handle highly unbalanced object sizes and complex topological structures. The MS-RED network, a multiscale residual encoding and decoding network designed for skin lesion segmentation, is introduced. This model leverages hierarchical feature extraction and residual connections to improve segmentation accuracy. Graph-Cuts loss, a novel loss function aimed at boosting model accuracy and generalizability for medical image segmentation tasks, is also explored. This loss function utilizes graph theory to optimize the segmentation process, enhancing the model's performance on unseen data. The CL-Dice loss function, a topology-preserving loss function for tubular structure segmentation, is discussed as well. This loss function has been shown to significantly improve segmentation accuracy in tasks involving complex structures such as blood vessels and airways. Deep residual learning for image recognition is also explored, which uses residual connections to alleviate the vanishing gradient problem in deep neural networks. This technique has been instrumental in achieving state-of-the-art results in various image recognition tasks. PyTorch, a widely used deep learning library, is discussed as a tool for implementing these models efficiently. Its imperative style and high-performance capabilities make it an ideal choice for researchers working on large-scale image datasets like ImageNet. Bidirectional Conva LSTM-U-net with densely connected convolutions is another model discussed, which integrates convolutional LSTM layers and dense connections to enhance segmentation performance in spatiotemporal data. The Highformer model is presented, which utilizes hierarchical multiscale representations using transformers for medical image segmentation. This model leverages self-attention mechanisms to capture long-range dependencies and improve segmentation accuracy. FatNet, a feature-adaptive transformer network, is introduced for automated skin lesion segmentation. This model adapts to different feature scales and spatial contexts, leading to improved performance in challenging segmentation tasks. The paper concludes with a discussion on the global transformer and dual local attention network, designed for retinal vessel segmentation. This model combines global and local attention mechanisms to capture both macro and micro features, resulting in enhanced segmentation accuracy. Finally, the authors discuss various loss functions, including the exponential logarithmic loss and generalized Dice overlap, which are essential for handling highly unbalanced segmentations in medical imaging. These loss functions have been shown to significantly improve model performance in such scenarios. In summary, this paper provides an extensive review of cutting-edge techniques in medical image segmentation, highlighting their strengths and limitations. It serves as a valuable resource for researchers seeking to improve their understanding of current methodologies and develop novel solutions for challenging segmentation tasks.